everyone. I'm Jay Dietrich. I'm a distinguished engineer at IBM working on energy and climate stewardship policy issues. I'm also the chair of the Green Grid working groups for doing Cert analysis and Emerald analysis. Cert is a performance power test method for testing server efficiency. Emerald is the test for testing storage product efficiency. We'll get to know a little bit more about those today in the call. And the title of today's roundtable is the tyranny of bad metrics. What I want to discuss is the strategies for assessing data center IT equipment energy efficiency. All right, so this is interesting. My apologies, I appear to be stuck here. There we go. All right. So what I want to cover today is the following. We're going to start out taking a look at the general regulatory landscape today regarding IT equipment. There's a lot of things happening in that space right now. And within the context of those regulatory initiatives, what I want to look at is what's the current market and the deployment strategy for IT equipment into the data center, and evaluate that transition to the cloud and virtualized data center models. Then peeling off of that, looking at how different server characteristics have changed and developed over the last 5 years, from 2012 to 2017, and how that affects that regulatory focus moving forward into the future. Then looking specifically at how idle power and active efficiency assessments are positioned to assess server energy efficiency and look at that in terms of the deployed power analysis, which is a validation method that the Cert working group has developed, and it's an effective way to assess what's the power demand of the servers when they're put into a data center to run a workload. And then look at the individual metric options and what outcomes those drive for energy savings. I'm also going to do a short discussion of storage product assessments and some of the activities that are going on there. I'm focusing on servers because we're further along in that analysis, but there's also clear patterns in servers that allow for a efficiency assessment. In the storage area, it's much more complex and much more difficult, and then finally a call to action, a set of conclusions. First off, I want to acknowledge the members of the Cert analysis working group. The data you see today is a collaborative effort of myself and this working group. Gary Verdon from Dell has done the yeoman's work on data management and data presentation. He has really facilitated much of the data work you'll see here today. And then we've got contributions from David Reiner, Shahid Sheikh, Stephen Eastman, and Jeff Doolittle, and you can see their companies there. But without this group and the work they've done, the information and data you see today wouldn't be available. All right, this is weird. Sorry, I'm having problems moving the screen here. All right. So from an energy efficiency standpoint, we've got regulatory developments occurring both in terms of procurement requirements, and that's occurring for products and for the data center. And then there's market entry requirements specifically to IT equipment products. And so what jurisdictions are those in? The EU is doing Lot 9, market entry thresholds for server and storage products. We've got and that set of regulations is on a timeline to have final regulations published late in 2018 from the current schedule, and which would see them going into effect probably in very late 2019 or early 2020. Green procurement data standards, the EU procurement standards for data centers has just gotten started. There's a task document that's released. There's comments due on this Friday, December 8th. So this is going to be on a little longer timeline. It's in the early part of the study timing for the EU process, but it's an important area to watch, and it will pull in the results of the Lot 9 activity. China Energy Server Energy Efficiency Standard, there's work going on there. That's more likely to finalize in 2019 on current trajectories, but things could move faster unexpectedly. And that, again, is setting a market threshold as well as some top runner categories for procurement consideration. And then Energy Star for servers is currently doing version 3, and that is expected to have a final draft or published regulations probably third or fourth quarter next year, going into effect mid-2019. And all these jurisdictions are looking at idle power and active efficiency metrics for the server and storage products, and then providing PSU efficiency. For today's discussion, we're going to focus on the idle power and active efficiency metrics. Why is this important? Why should data center operators and equipment manufacturers be paying attention to these activities? As data center operations become increasingly virtualized, we're seeing that the performance and power capabilities of the servers are becoming more and more important. We're driving to higher utilizations. You're seeing small and medium enterprises shifting away from office and closet installations and into cloud environments. And we're seeing an increased emphasis on server performance and driving higher utilizations. So from that standpoint, we find that idle power, which has been a focus item initially, because it was an easy thing to measure, and we'll look at some data that shows early on idle power was very high on server products, but it correlates to performance, but it does not correlate well to performance and power. And that's looking at all levels of power use. So we'll assess this at idle power. How does the system perform, or what's the deploy power of the data center at idle power, all the way up to 100% power. And so where we're looking then is on the active efficiency metric, which is doing a performance to power metric that gives you a look at what's the workload that you can deliver per unit of energy consumed. And when you look at the database, the available database on the Cert scores, you see a wide variation in servers with similar characteristics in what their performance power scores are. So we feel it's an effective way to assess and review how server efficiency, and we'll get into the details on that. So let's start by looking at where's the market going, where does it sit today, and where do we see it in the 2019-2020 timeframe when these regulations will go into effect. So if we look at the DOE study that came out in 2016, the general view is that over time, moving out through 2020, data center energy consumption is going to increase at a couple % a year. But there's opportunities with the implementation of more efficient integrated products and greater use of consolidation and virtualization, both on an individual level and also through workload management software, that there's a potential for that power consumption to actually tail off a bit. A good example that I can give you is for IBM's data center operations over the last 5 years, and these are enterprise data center operations. We've reduced the server footprint by 25% while doubling the workload, the applications and images that are supported on that footprint. So, and we're doing that both through optimizing the use of the capabilities of the servers, but also through the use of automated data workload management systems that allow you to assess and optimize workload placement across a whole server infrastructure, a data center system infrastructure. I will note there are competing viewpoints to the DOE study. There was a Fraunhofer Bordercept study in Germany that showed a much higher, 4% plus per year data center energy use growth. So there's different views on this. I think in general, from an industry standpoint, we feel that the continued emphasis on going to cloud, using migratable workloads that can be placed where they're most efficient and moved to optimize utilization is going to drive the market as we move forward. And that in turn suggests that we need the high performance servers to be available in the marketplace. So let's look then where, so we've looked now at what are some projections. How is the workload going to be delivered? And this is IDC data from their quarterly cloud infrastructure tracker, first quarter 2017. And this is the value of the marketplace as compared to enterprise and cloud. And we see a continuing movement to cloud, with public and private cloud expected to represent about 52% of the total market by value in 2021. And so we see this shift coming and believe that this is going to be driving systems that have higher utilization. It's going to be pulling in smaller and medium enterprise data centers into these managed spaces where companies are able to procure their hardware and their software as a service rather than having to manage it in-house. There's benefits to that to many companies, and we're seeing that transition develop and move forward. So how then does that translate into hardware sales? Again, this is IDC quarterly tracking data. And what we see, if you look at the blade and tower data on the left, the percentage of sales there dropped from 32% of the market to 17% of the market from 2012 to 2021. While we see the multi-node and rack servers increasing and picking up that percentage, that 15% reduction. So we're looking then at, again, the migration of the marketplace into the cloud services, the optimized rack and standard rack to drive cloud and highly virtualized installations. So now we've seen what the marketplace looks like, how we are viewing the move of the into a more virtualized environment. Let's look at how the servers have been performing over the last 5 years. So this is the spec power SSJ. It's a metric that measures performance, divides that performance into 8 intervals, and then measures performance and power. And so what I've plotted here is, what was plotted for me by the spec power committee, is the idle power, and you see that, that's the interface between the light blue line and the dark blue line. Maximum power, which is the dark blue line, and then performance, which is the black line. Just as a note, these systems are typically built as minimal systems. They have the minimal memory and storage devices needed to run it. They run a low-end processor, and they're configured to optimize to this the spec power SSJ. But what we see is that in 2007, when the focus really started on these data center products, we had very high idle power, relatively high idle power, and a very small dynamic range. The difference between the maximum power and the idle power was about 60%. And so then you see over the next 3 years, from 2007 to 2010, a significant effort on the part of server manufacturers to reduce that idle power and to increase the dynamic range. And you see that then increasing over time, with idle power staying relatively flat from 2010 on, while maximum power is increasing, and we're seeing performance increase at a rate of about 10x. So again, these are all averages, but there's significant variation around the mean on these. But in fact, what we're seeing is that server designers are improving the power scaling increasing the amount of reduction they achieve as power reduction as the utilization drops, and getting and driving higher performance in the systems. Now let's look at the ITI Green Grid CERT database. So this is data that's been collected by EPA and by ITI and Green Grid of systems that have been certified to Energy Star or will be certified in the case of the 2017 systems. So the data set on this particular graphics, we've got 52 server products with roughly 4 configurations each. There's a low-end configuration, a pair of those low-end and mid-power. Those use the lower-end processors in the process family. They have lighter memory, typically 16 to 64 gigabits of memory, and they'll run 1 or 2 storage devices. At the high end, configuration will be the high-end processor. You'll have a much larger memory installed depending on the processor capability. That'll run typically from 128 to 256 to 384. Again, 2 or more storage devices. And then there's a typical, which is meant to represent the server of that particular family, the configuration that's most often sold into the marketplace. So there's 2 important things to observe here. The first is we see that these servers, which are configured across the full range of the type of servers that will be purchased, show a flat idle power over time. One important point is that with the 2017 release of the Skylake processors, we see a jump in the idle power on the high end. And that's the result of the newer processors that'll have between 18 and 28 cores in the high end of the family. And you've got TDPs, the socket TDP is 180 to 205 watts. So these are substantially higher power use and higher performance processors than were available in the previous generation of processor families, and they support a more complex ecosystem of memory and storage devices. But in exchange for that power, we see a significant increase in performance. Again, looking at the 2016 and 2017 data as compared to 2012, 2015, those newer processors, the late model Broadway and Haswell, I think, in 2016, those make up the 2016 data, and then the 2017 is the new Skylakes. And you see a performance improvement. So how then does that translate into active efficiency, the performance over the power? And again, so what we see is a significant improvement in that active efficiency as measured by the CERT test from the 2012 to 2015 products to the 2016, 2017 products. And this is consistent with work we've done to look at how new generation processors affect the active efficiency score, performance, and idle. And so in general, then what we're seeing is that as new servers have been released based on new processor and memory technology, we're driving higher performance, keeping idle largely flat, and driving then better active efficiency because of you're getting more performance on the same amount of power. All right, so then looking at idle power and the active efficiency metrics, how do those perform as metrics for assessing server efficiency? So in the regulatory discussions, and I've alluded to this, there's really been 3 main areas that we've been focused on as being potential metrics to assess server efficiency. The first is idle power. That comes from the original work of Energy Star. And in the time frame when Energy Star started and when we began looking closely at how do servers perform, idle power was an easily available metric. The next, and what the Green Grid Working Group is pushing to is to move to the active efficiency metric because it's representative, it incorporates performance. Idle power has no performance metric incorporated into it, and in fact, we'll find that from an efficiency standpoint, it actually negatively correlates. And so we can do the active efficiency, which we think there's strong technical reasons for doing that. The other metric that's being looked at, which EPA published in draft 2, is a combined idle power and active efficiency metric, where you break out both at a minimum active efficiency, but then you're also trying to identify products that have high idle power and so not as good at power management, and therefore should not be identified in the marketplace or recognized as a high-performing server under Energy Star. But the other piece of this is that it's really important to look at, if I have an individually efficient server or a server with low idle power, what happens when I deploy that server into a data center to perform a workload? And you've got to look at the system implications of the individual products to understand what's going to happen in the data center. So so we're going to take a look at that as we move through this analysis to understand how a system assessment is important to assessing efficiency. So let's look specifically. Idle power, we feel is not suited to assessing server energy efficiency. It correlates very highly to component choices. So better performing, higher power processors, larger memory capacities, larger drive counts drive higher idle power because of the nature of the components and the fact that you've got a certain amount of base power. It does, but because as your components draw more power, you're getting more performance, you do see a correlation between idle power and performance. And these are some of the Cert workload scores, and we see that idle power correlates fairly well to performance, but on the CPU workloads, the 3 on the left and the 1 on the far right, there's a poor correlation to active efficiency. You do see good correlation on the flood and memory scores, and that's because as you increase the memory capacity and the number of storage devices, you also increase the efficiency measurements of those products. So quickly, just a quick primer on Cert. What Cert does is it has 7 CPU worklets, 2 storage worklets, and 2 memory worklets. The test suite identifies the maximum transaction rate for each workload, and then divides that transaction rate into 4 intervals for the CPU scores, 8 intervals for the hybrid SSJ, and then 2 intervals for the storage and memory scores. And so then you measure performance and power, and at each workload level, you combine those together. You take the geo-mean of the power and the geo-mean of the performance, and you divide it by the geo-mean of the power. That gives you a workload score. Then for the workload scores, you combine by workload type, CPU, storage, and memory. And again, you do a geometric mean of those individual workload scores to create a workload score. So that moves you up to the workload section. And then we do a weighted geometric mean of 65% CPU, 30% memory, and 5% storage to create a single aggregate score. A lot of work went into identifying the 65-35 allocation weightings. That was an effort between Green Grid and Spec Power. If somebody's interested in getting more details on that, they can contact the Green Grid Working Group. So in general, that's how the Cert works. The important thing here, and I just want to touch on, is from a dynamic range standpoint. So the difference between the maximum power and power at 25% or idle power, the Cert test recognizes and gives a higher efficiency score to a server with a better power management configuration. So we've got 2 servers here. This is an example. Both have a performance measurement of 1,000 on a given workload, and the maximum power for both is 100 watts. One server, though, is able to reduce 20 watts at each performance interval, while server B only drops 10 watts per interval. So when I take the geo-mean of the geometric mean of the power, I get a much lower average power for server A than I do for server B. on the same performance, and so my net workload efficiency is much higher on server A, 8.4, as compared to server B at 6.6. And so the important message here is that the Cert efficiency rewards those servers that have the best performance and also the best power management. And so that's really an important consideration in looking at what is my most efficient server. Again, just a different view of this dynamic range discussion. So this is, we're plotting active efficiency and idle power against 1 minus the ratio of P idle over P max. And you see that for the active efficiency score, we get better scores in general on the trend at the higher dynamic ranges. And we see that the dynamic range goes down as idle power increases because you've got, again, a much more heavily, your server has much more, many more components in the configuration, more base load and more idle power. The other point on this graph that I think is important is the scatter of the data. And so when you get into the individual configurations and the Cert measurements, what you see is a high variability in server systems. And so how they perform, how a server performs is very dependent on the design and the firmware. And so you'll see servers with very similar component loads with very different active efficiency scores based on their design. And so within the data set, we see that the active efficiency gives a good indication of a server that delivers more workload for each unit of power. And then this last chart now is what we're graphing is the active efficiency score against idle power. The point that we worry about and that the Green Grid Working Group has really been focused on are these high efficiency servers that show a high active efficiency metric with high idle power. And so when you go with a straight idle power metric, most of the servers in that red box will not pass the metric. Using the EPA standard of 25% passing, with the EU standard looking at a 75% passing rate, which is what Green Grid's been using as a market threshold indicator. You'll get more of those to pass, but you still lose a significant number of those. And this has become particularly important in light of the new processors with the higher TDP and higher core counts. And we did some assessments where we see that those new servers will fail on idle because of the high base idle power, while they'll be in the top 90% of the active efficiency. And so we've really been focused on highlighting this fact and making the case that to get the best performance in the data center, we've got to make sure that these high performance servers are available in the marketplace. So what's the basis for our view on that? And it's this deployed power analysis. So what we do with the deployed power analysis is we take the data that's generated by Cert and we create a geometric mean performance, average performance for each server using the Cert data. We then take we designated a workload value that was equal to 100 times the best average geometric mean workload score of all the servers. And then, so we use that as this is the workload we want to operate in the data center. So it's a synthetic workload, it's a synthetic analysis, but the intent is to look at how many servers of a given configuration do I need in the data center to run that workload. So we take the target performance, in this case, on this chart it's 12,000. We look at the weighted performance of the server, which is 39.7, and that gives us a total of 304 servers that are needed to do that workload in the data center. We then pick a specific power level, and we'll see in the analysis what we did was used the idle power, the geometric mean of the power load at the 25% interval, the 50% interval, and the 100% interval. So we look at how the servers perform at different utilization levels and what their deployed power is in the data center. So in this case, we've got 304 servers. Their weighted power is 357 watts, and so their total deployed power in the data center is 109,000 watts largely, or 109 kilowatts. We then, for the whole data set, those 52 products and 200 configurations, ranked the servers by efficiency and then by the deployed power. What's their deployed power in the data center? And we compared that ranking to understand how does the active efficiency rank match with the deployed power, how much deployed power that server is going to take in the data center. All right, come on. Hang on. Let's see. Okay. And these are two examples of the graphics that we ran. So these are the two-socket servers again. The top pair are the low-end configurations. So you see we've got the deployed power running here with the active efficiency score. This is version 1. I had to use some charts we had already generated. So this is doing a threshold, an active efficiency threshold with a 25% yield, and we see that we get a very clear differentiation. The servers with the lower active efficiency score would drop out, and we maintain those servers with the higher active efficiency score. When I use an idle limit, we get a much different breakout. And so we see that idle limit is taking out many of the servers that have a high active efficiency score because of that, the fact that you've got more base power on systems with the higher component loads. And this is accounting for idle adders for memory and for storage devices. So this is using the EPA methodology. Similarly, if we look at the high-end configurations, we see the same breakout differentiation using active efficiency versus idle. And so just applying this example then to a situation using the data, and I will acknowledge that the servers we selected are on we've got one high active efficiency server and one low idle power server. So server A passes the idle limit, a straight idle limit, but fails an active efficiency limit. And this would be to drive a 25% exclusion. So this is a 75% pass rate. So server A, again, passes on idle limit, fails on active efficiency. Server B fails on the idle limit, passes active efficiency. When we look at the deployed power of those systems and the number of servers you have to put into the data center to do a defined workload, we see that the server with the higher that passes the active efficiency needs significantly less units and significantly less power than the server that passes on the idle limit and fails on the active efficiency limit. And so the point of this chart is just that we've got to look carefully at what the impact of the thresholds are on the server selection and which servers get selected and excluded in a given test, because you can get an outcome that will result in higher data center power use. So what are then the different options, and how do they manifest in terms of energy savings? So we've talked these through. These are the 4 metrics that we're looking at and have been assessing. We've talked about the active efficiency metric. We've taken a combined idle power and active efficiency threshold, so you have an idle power limit and an active efficiency limit. We've also done an idle limit with a performance allowance, so we're calling this a modified method. And what this does is it provides a system performance adder on an idle power limit to recognize the difference in capabilities and power draw on servers that are using higher performance processors. And so this gives some weight to the fact that a server with higher idle power oftentimes will also have higher performance. And then the final is just the straight idle limit which is done in accordance with the current Energy Star procedure from draft 2, which is also the procedure in draft 1. And what we did was we ran a calculation of, in this case, it was a 25% pass rate for the four different approaches: a straight idle, which is the light red bar on the left, the modified idle with a maximum difference of 40 watts between the highest performing processor and the lowest performance processor for the system adder, the combined efficiency and idle metric, which we see in purple, and then active efficiency in light green. And the important takeaway here is that using active efficiency significantly reduces the deployed power in the data center. And on the particular metric we're doing with the 25% pass rate, we see that the idle, incorporating an idle metric does drop out some of the servers, higher performing servers that have higher idle power and lower power management. But pretty much for the combined efficiency and active efficiency and idle metric and the active efficiency, you get a good balance between the getting the server efficiency and also dropping, making sure that the deployed power is low. But the main message here in this chart is the impact of using idle power significantly reduces the number of high-performance servers available in the data set. So this calculation is done by taking the average power use of all the servers that pass and the performance and doing this calculation. And you'll also note that we did the calculation for a deployed idle power and then deployed power at the 25%, 50%, and 100% utilization point. So we're looking at the full range of the server operation, and we see that the active efficiency and the combined metrics give a better overall, much lower deployed power in the data center. So now looking at the same, looking at a different approach, which is projected energy savings, based on this would be a 75% pass rate on the data set. And again, we see the same general result, which is the combined efficiency and the active efficiency provide better energy savings in the market, give better preservation, assure that the higher performance servers are incorporated into the market, that their value is recognized. Right. So that's the full discussion on the storage, or on server products. What I want to do is just do a quick review of storage products. I've got 3 charts here. So again, we've collected data from systems that are certified to Energy Star. The table in the bottom right-hand corner shows you the number of families and configurations we have for each of the online categories that are in the Emerald analysis document. Online 2 servers are typically, you have 12 storage devices. Online 3 is up to 100, can support 100 or more storage devices at maximum. And online 4 are systems that support 400 or more storage devices at maximum capacity. And what we found is that storage products in general are extremely complex and difficult to assess for efficiency. First of all, we find that when you look at the data, and we were able to collect idle data for many of the systems that have been tested, because of the maintenance and functions that run on a storage system, the idle, there's not a large dynamic range on products. In the systems that were tested in this data set, the dynamic range is 2 to 20%, or put another way, idle is between 98 and 80% of the maximum power. So because of the spinning disks, and even in systems with SSDs, so this represents both SSDs and spinning disks, the amount of work going on and the way the systems are configured don't generate a lot of idle power. idle power savings. On the metrics that you've got, the one, again, looking again at the idle metric, which is a watts per gigabyte metric, and the EU point systems, two task documents, the task 4 and task 5, point systems for storage product documents, recommends as the metric for storage products watts per gigabyte. And this is not a good choice. It's a poor indicator of efficiency, because this is driven by the fact that the numerator increases with higher speed drives, and those are the ones that provide you the best performance. The denominator increases as you increase your capacity. And so what the watts per gigabyte metric ends up incentivizing is the low power disks, a 7.2K RPM disk, with a high capacity of 4, 6, or 8 gigabytes. And so it does not bring you the most efficient storage product, and it pushes you really to data tubs. And we'll look at some of just one example of the data analysis, but when you look at the products and the data that's been posted in Energy Star, and we've worked on this with the storage network and SNEA group, there's just no clear trends from the Emerald test data regarding storage efficiency, and this is driven in part by the fact that the IOPS for watt score is dependent on a whole set of variables: the drive type, form factor, speed, capacity, how many controllers you have, what the performance capabilities and cache sizes are on those controllers, the overall drive count on the system, because if I've got a low drive count, I'm amortizing my controller power over a fewer number of disks. As I get to a higher number, of disks, I'm better amortizing that power. And so there's a lot of variables and a lot of difficulty in sorting it out. I apologize, this chart is an eye test, but what I put it in for is this is all the data on Line 3 storage products transactions testing. And you test on this test for 3 things: the write workload, the read workload, and then a hotband workload. And Energy Star is assessing the hotband workload because it's representative of a dynamic transaction environment on a storage product. And when you look at all of this data, you see what I comment on the other chart is that the results really depend on the system configurations, the drives used, and the system architecture. And when you get into the individual data, you see things like systems that have previous generation and next generation technology controllers with the newer generation controller having significantly better scores. The drive, picking different drives because of their power and performance characteristics will deliver an optimum point. So because of the level of the variables, we've just found that it's very difficult to make any kind of an efficiency assessment like we've been able to do with servers. So where do we stand on this? The current view is that the Emerald results are an indicator that they should be reported, but trying to do a specific assessment based on those results is not going to be effective with the data we've seen to date. We're also seeing that in many cases that storage product efficiency is dependent on the capacity optimization methods deployment. So if I can, for example, use compression and deduplication on a particular data set where that's a significant benefit, the implementation of the comms adds power. It reduces idle time to almost 0 because of the ongoing work that the system does to do that compression and deduplication. But overall, it significantly reduces the footprint of the product in the data center and lets you store more data for each drive or device that you have on the system. And so you've got so the comms add a whole nother variable into that assessment and what helps make the system more efficient. And so the concern here is that the EU initial assessment on the Task 5 document for storage systems that suggests the use as ready idle as an efficiency measure is going to result in some bad outcomes. It will bias against those high capacity low speed systems, and it is biased against the high speed high response systems that you need for transactional and sequential workloads. So what, in summary, conclusion, how can you participate in driving change? I think the industry needs to work to highlight the importance of performance in assessing efficiency, and the fact that as we move forward in the marketplace, the focus both from the equipment manufacturers and from data center operators is to drive higher capacity utilizations and better consolidation and deployment of the systems of the products within the SLA, the serviceability requirements of a customer, and that's going to result in some idle time for servers, but we think that's going to be less and less, and that's going to be helped by these workload management tools that we're seeing coming in. There's several companies that can survey the whole data center floor and optimize workload placement based on system capabilities and the SLAs. And so we've got to be highlighting the importance and the relevance of those tools and the need to have the right servers with the right performance, the right storage products with the right capacity and capabilities available in the marketplace to let us optimize the data center footprint. And then we've got to continue to work to make the point that in order for us to innovate and operate efficiently, we've got to look at the individual products, and we recognize that, but we've also got to look at how they perform as a system in whatever environment they're in, because you're selecting the system in large part on its performance and what you need for your maximum performance on the most important day of the year or on the most important day of the week or wherever it might be. And so you've got to have the performance capability. What then matters is that you're doing that performance with the lowest average power, and that's what the active efficiency score brings you. And I encourage the group to become familiar with some of the documentation and activities that are going on and become engaged in supporting workable approaches that drive better efficiency and reduce the power demand of data centers in line with what we saw in the DOE study, while still making the high performance, high capacity products available in the marketplace. So thank you for your attention. We can do questions.
Hi Joe, we haven't had any questions through yet. If anybody wants to ask any questions or touch on any of the issues raised in the presentation, do please send me a message now. In fact, I lie, we have had one through just now. The question is, have you measured or thought about cluster services like 4-in-1s?
So I need a little more help.
Okay, hang on, we're just getting a message for you here. Apparently 4-in-1s have higher idles. I presume that means either they have high idle power metrics.
4-in-1s. Henri, I still don't understand. I'm sorry.
Sorry, this question has just come through to me. Sri, if you could just send me more details about what you'd like to inquire about, and I can relay that on to Jay. Does anybody else have any questions? We'll keep this open for a few more minutes, and if you have any questions, do send them through, and I will forward those on to Jay. Thank you. Hi, Jay. We have more information on that question. Sri clarifies that there are 2 used servers that are actually 4 nodes, and he's measured them, their idle power at about 450 watts, but they have the performance of 4 servers. So his initial question was about, have you measured or forced back cluster servers, like these kinds?
So we do have measurements for, yes, we do have measurements for multi-node servers, and those get handled, they have a specific category under the regulations because of their unique architecture.
Okay, that's interesting. So Street's just asked us, with these kind of servers, would the SERT, the CERT metrics readily apply?
So yes, they do. You can analyze them under the CERT metric.
Okay, well, thanks, Jay. If anybody else has any more questions, please do send them through. We'll be on here for just a few more minutes. We've had another question through, Jay, from Doug. He asked if there is a CERT online database available as there is for spec power.
There is. So we've made it available to all the regulatory agencies, and EPA has been releasing it. So if he sends me an email, we can get him the connection to it.
Okay, Doug, if you send me your email, I can link you up with Jay on that one. All right, we'll leave this open for a few more minutes. If anybody has any questions, we'll close the discussion at about 5 to 4. So any other questions, if you can let us know in the next 2 minutes, that'd be great. Otherwise, if you have any questions after we close the actual webinar, we will firstly be circulating the webinar. We've recorded it. We will be circulating it out to all of you, as well as those who didn't attend the event. And you can follow up with us and ask us any questions, and we can link you up with Jay. So any other questions, just come to us now or later. Okay, Jay, I think it's probably about right to wrap up there.
Okay.
Thank you all for attending. Thank you, Jay, for your time. As I said, if you have any further questions about any issues raised on the webinar, or indeed any other questions about the Green Grid, please get in touch. You can get in touch with us at thegreengrid@spreckley.co.uk. And thank you all for attending.